People are made of cells. Cells are made of molecules. Molecules are made of atoms, and atoms are made of electrons and protons and neutrons. And those last two are made up of 3 quarks. Simple stuff, right? Well, all except for that last part. Protons and neutrons are actually made of many, many quarks and just happen to look like 3 quarks when you look at them in a particular way. And even then, sometimes they're made of 5 quarks, including the charm quark. The humble proton may seem simple enough, but it's certainly common. Most of the visible matter in the universe comes from protons, either as lonely hydrogen nuclei or bound with neutrons into the nuclei of the various elements of the periodic table. You'd think by now we have a pretty good idea of the properties of the proton, but actually their interiors remain a profound mystery. It wasn't until the late 60s that we even confirmed that protons were themselves not elementary particles, but consist of 3 quarks. Now, thanks to AI, we have evidence that suggests they may be made up of 5 quarks, at least sometimes, 2 of them heavier than the proton itself. To make sense of this, we need to understand how physicists probe the smallest scales of nature, and that means understanding the physics of scattering. Every time you open your eyes, you're performing a scattering experiment. Photons from some light source, like the sun, bounce or scatter off objects in the world around you into your particle detectors, aka your eyes. Your analysis computer, aka your brain, then builds up a color map of the world around you based on the properties of those photons. Well, it's also possible to see the subatomic world if we do a different type of scattering experiment. In general, the higher the energy of the scattering particle, the smaller the object you can see. To see subatomic scales, it's better not to use photons at all, but instead to use particles of matter. That's how Ernest Rutherford discovered the nucleus. He shot a beam of alpha particles, which we now know to be helium nuclei, and a thin gold foil. He found that while most of those particles passed straight through, a small fraction scattered off something very small and very dense. That's how he figured out that the atom is mostly empty space, with most of its mass concentrated in a tiny central nucleus. Since Rutherford's 1911 experiment, we've gotten much better at doing this. For example, we now have electron microscopes which shoot electrons into a sample and measure how they're deflected. Sophisticated software then reconstructs the structure of the sample, just as our brain reconstructs the structure of the world. Electron scattering can be used to study the structure of anything larger than an electron. Well, that sounds pretty useful because electrons have no size, they're point-like. But actually, not so fast. Electrons are quantum objects, and so have a wavelength that gets shorter the more energy the electron has. So really, I should say, electrons can be used to study anything that's larger than the electron's wavelength, which depends on energy. So if you want to study the interior of a proton, you need a pretty high energy electron. Below a certain energy, the electron will just bounce off the proton as a whole. But with enough energy, the electron will punch into the proton and then scatter off the proton's internal parts. I should add that such an electron is energetic enough to destroy the proton, which sounds bad, but it's actually okay. Sometimes you need to break something to see what it's made of. And that's what the physicists at the Stanford Linear Accelerator Center, SLAC, managed to do in the 1950s and 60s. They accelerated electrons to higher energies that had previously been achieved and slammed them into protons. Then they watched what came out the other side. In 1968, they published their results. From those scattering products and the deflection of the electrons, the SLAC physicists deduced that protons must be made of 3 point-like particles. These particles match the properties of the so-called quarks, theoretical components of nucleons proposed by Murray Gell-Mann and George Zweig earlier that decade. And that's how we get the proton model that you're probably familiar with, 2 up and 1 down quark, with 3 different charge colors bound to each other by gluons carrying the strong nuclear force, as we've talked about in previous episodes. And same for the neutron, except it's 2 down and 1 up. I'll be talking about protons from now on, But everything I say probably applies to neutrons too. While the slack electron beam was the most energetic of its time, we quickly figured out how to make more and more powerful accelerators. And as we did so, we started to see something strange. Remember I said that higher energy scattering allows us to see smaller things. That means finer resolution. Well, as we powered up our accelerators, that's exactly what we saw, the detailed guts of the proton. And it turned out to be much more complicated than just three quarks bound to each other. The interior of the proton was revealed to be a complex cluster of energy, a dense network of gluons that are constantly transforming into pairs of virtual quarks and antiquarks, which quickly annihilate each other, turning back into gluons. We call this the Quark Sea, and this constantly shifting, flickering mess is a stormy ocean indeed. But because the quantum properties of charge and spin and color must be conserved, there is order within this chaos. If you took all the contents of the Quark Sea at one instant, you could list all of the quarks and all of the antiquarks and see that they cancel each other out, except for two up quarks and one down quark. These valence quarks will constantly exchange energy and color charge via the Quark Sea, and may even be annihilated by a virtual particle or antiparticle, but are instantly replaced by that virtual particle's partner. These valence quarks are what the first slack experiments detected. But as we increased the electron beam's energy, those electrons started to interact with the transient entities of the Quark Sea. They scattered off gluons and virtual quarks, revealing that complex inner structure. The higher the energy of the electrons, the more fine detail we saw. We saw the virtual up and down quarks of the Quark Sea, the gluon network, but also some weird stuff. For example, around 1% of the time there was evidence of a charm quark inside the proton. That's odd. The charm quark weighs more than the entire proton, 36% more in fact. It's like opening a 1 kilogram box of, apples, and finding a 1.3 kilogram melon inside. Fortunately, there's a perfectly plausible explanation in the case of the proton. It turns out that the particles we discover after smashing an electron into a proton aren't necessarily inside the proton to start with. That's because the energy carried by the electron can create brand new particles. Remember, E equals mc squared, which tells us that mass and energy can be converted into each other. As the ingoing electron transfers its substantial kinetic energy into the Quark Sea, new particle-antiparticle pairs can be created that were not part of the proton to start with. As the energy of the electron beam increases, we get a scattering signal from finer and finer structure, but this signal is increasingly muddied by the new particles created in the collision. We call the particles that are inside the proton to start with intrinsic particles, and they include the valence quarks and the virtual quarks and gluons of the Quark Sea. On the other hand, we call the particles created in the collision itself extrinsic particles. After a particle collision, we see both intrinsic and extrinsic particles, as well as the decay products of those particles in the cases where the outgoing particle is too unstable to reach the detector before falling apart. So if the ingoing electron has enough energy, perhaps it could produce the charm quarks that are detected in some cases. If the charm quarks are extrinsic this way, then there's no problem. But even early on, there was some evidence of intrinsic charm quarks in protons. There was the hint of the presence of charm quarks even in cases where the electron didn't carry enough energy to produce one. So if the charm quark is too massive to be produced by the incoming electron, and is too massive to be a regular part of the entire proton, how can it exist? Well, it's not quite as simple a conundrum as I make it sound. As you reduce the energy of the collision, the probability of finding an extrinsic charm quark also goes down, but only reaches zero at zero energy, which means when no collision is happening. In these early experiments, charm quarks were appearing only slightly more often at low energies than expected from calculations, and so the evidence for intrinsic charm quarks was weak. Let's talk about those calculations and how they're done to see why this uncertainty exists. The interior of the proton is the realm of the strong nuclear force, which is described by quantum chromodynamics. With its multiple different charge types and different charge carriers, QCD is far more complicated than, say, the single-charge electrodynamics. One weird thing about QCD is that the calculations are easier at higher energy than at lower energy because it's easier to implement a favorite hack of quantum mechanics called perturbation theory. That means it's easier to calculate the result of a high energy scattering than a low one. It's extra hard to properly calculate the state of the interior of a proton in the absence of any collision. For this reason, it's kind of straightforward to explain all the extrinsic quarks that we see at high energies, but it's very difficult to explain the behavior of the 3 intrinsic quarks we see at low energies, and it's even harder to explain why we seem to find these charm quarks at those same low energies. Although it's hard to model the interior of a proton at low energy, our intuition still tells us that it shouldn't contain things more massive than the proton itself, like the charm quark. But there is actually a way to get quantum chromodynamics to give us intrinsic charm quarks. We do that by taking advantage of the Heisenberg Uncertainty principle, which, among other things, tells us that we can borrow energy from out of nowhere to create massive particle-antiparticle pairs as long as those particles vanish again very quickly. The more massive the particles, the shorter they're allowed to live. For this reason, it should be possible to generate a charm-anti-charm quark pair even inside a proton as long as it exists only for a very short duration. Due to the large mass of the charm quark pair, their momentary appearance is a bigger deal for the proton's inner structure than is the continuous flickering of virtual up and down quarks. In that instant of their appearance, the proton looks more like a 5-quark particle than a 3-quark particle. However, I wouldn't go so far to say that the proton is briefly more massive. The proton's measured mass comes from the average of its internal energy over the time of measurement. So if the charm quarks only exist for a tiny fraction of the time, then they only contribute a fraction of their own hefty mass to the proton's mass. I just gave a crude outline of the theory of intrinsic charm proposed by Stanley Brodsky in 1980 to explain the weak evidence of charm quarks in protons. But proving this was challenging due to the difficulty of modelling low-energy particle collisions. One issue is that there are typically many different models of the proton interior that can lead to the prediction of the same scattering results. So you might come up with a model that includes intrinsic charm that gives you a perfect match for your average particle output over many collisions, but you may have gotten that model right just by chance. And if you analysed even more collisions, you'd realise that the correct model was actually totally different. Without testing all possible models, it's impossible to know whether a model of intrinsic charm is really better at predicting the outcome of these collisions versus some unknown model that doesn't include intrinsic charm. So now you have a better idea why there was so much uncertainty about the existence of charm quarks in the proton. It just wasn't possible to sift through all the possible models to be sure that intrinsic charm was needed to explain the scattering experiments. That is until artificial intelligence came along. This new tool allowed scientists in the NNPDF collaboration to do something that was previously impossible. Instead of testing one model, they could test hundreds of thousands of models of the proton interior at the same time. They trained a neural network to analyze nearly 30 years of proton collisions, not constrained by a single model, but in the limit of all possible models. The network was then able to create new models that approach the scattering data as closely as possible. This was incredible. Instead of a few scientists trying a few models every couple of years, they could have this machine test thousands of models in just a couple of days. And while a scientist may be biased to trying to find evidence in favor of their favorite model, the network just wants to find a best answer, even if it contradicts intrinsic charm. And now we get to the punchline. This neural network was able to find a model with intrinsic charm that predicts the data much better than any previous model. Now, currently this is still tentative. the team reports a 3 sigma result, which means a 1 to 1,000 chance that they found the wrong model in favour of intrinsic charm just by random chance. Of course, the gold standard for claiming a victory is 5 sigma, which means a 1 in a million chance that the result came from an unlucky streak. That sounds like a high standard, but with so many different experiments happening around the world, we do get a lot of 3 sigma results that end up being wrong. So, will this one pan out in the end? Will we find the charm quark in the proton? The melon in the apple box? Well, we'll need to blast a lot more protons to find out, but we may also get closer to our answer by improving this shiny new tool of machine learning. That technology is developing at a rapid pace, and it's increasingly used across all areas of experimental physics. Computers can come up with and test models much faster than any physicist, which means the physicists can get on with the more interesting work of interpreting successful models. Wherever we land on the intrinsic proton charm, there is something charming about this cooperation between artificial and natural intelligences working towards the common goal of deciphering the inner workings of space-time. Hey everyone, comment responses will return next week, but if you really want to watch me try to answer difficult questions with mixed success, head over to Star Talk, where my longtime colleague, Dr. Neil Tyson, tries to stump me with some real doozies. Link in the description, and feel free to tell them we sent you.